Step-by-step telephone switching systems employ three major types of switches: line finders, selectors, and connectors. This video details the operation of the selector, which you are looking at now. It's the predominant switch type in the step system. The purpose of a selector is to process one or more dial pulse digits and establish a connecting path from its preceding circuit through itself and to its succeeding circuit, and maintain this connection for the duration of the telephone call. This is a digit absorbing selector, which means it has the capability to process more than one of the dial digits on a given call. In this video, we will only be looking at its operation in a non-digit absorbing mode, that is, when it only processes one digit of a call. The digit absorbing feature is detailed in a separate video. This type of selector was used in the Bell system, and it was manufactured by both Western Electric and Northern Electric. This particular unit was manufactured in Canada by Northern Electric. The equipment and schematic drawing number for this switch is 30976, as you see stamped here on the switch base. This switch was manufactured in 1962. Some of the apparatus is date stamped, as can be seen here on three of the relays. The 62 indicates year 1962. The horizontal bars preceding the 62 indicate the quarter of the year. 1 bar for first quarter, 2 bars for second quarter. The number letter combinations below the dates are the manufacturer's codes for the relay types. The manufacturer's code for the switch type is 197EU, as can be seen here stamped on the top of the switch frame. Most step-by-step switches were type 197, including line finders, selectors, and connectors. The three main structural parts of the switch are the switch base, the switch frame, and the switch cover plate. The iron plate at the rear of the switch provides the platform for mounting most of the switch parts, and this includes the 6 relays at the top of the switch, the switch frame, and the switch cover plate. On each side of the switch base there is a pair of these bayonet type mounting slots. These allow the switch to latch into position over lugs on the selector shell framework. So we're just going to quickly identify the major piece parts in the selector. Starting at the top, there are 6 relays. You can see them labeled here: A, B, C, D, E, and F. These 2 studs are called the cover guide studs. They help protect the relay contacts when the switch cover is being slid into position. So this post is the normal post. These 2 spring assemblies are the normal post springs, and this white plastic piece here is the normal post cam. Those 3 parts are not going to be discussed in this video. They are used for digit absorbing, which is the topic of another video. This is the shaft spring cap, the shaft spring bracket, the normal pin clamp, the normal pin, the off normal finger, the vertical off normal spring assembly. This is the shaft. This is the upper shaft bearing. This is the vertical ratchet. This is the rotary ratchet. This is the double dog. This is the stationary dog. Looking at the right side view of the top of the switch, we have the B relay heel piece with its spring assembly, the D relay heel piece with its spring assembly, and the F relay heel piece with its spring assembly. Moving down the right side, we have the release armature one of the vertical magnets, the double dog spring, the Z relay with its spring assembly, the 11th rotary step spring assembly. And here's a side view of the double dog. Looking at the left side top, we have the A relay heel piece and its spring assembly, the C relay heel piece and its spring assembly, and the E relay heel piece and its spring assembly. Moving down, we have the left side vertical magnet. We have the release magnet bracket. Here is the stationary dog. Here are the two rotary magnets and the rotary magnet armature. Here is the rotary interrupter spring assembly. And this is the rotary armature lever. I have removed the switch frame from my part switch so we could get a better look at some of the parts mounted in it. As you can see, it's a very heavy-duty cast iron framework. On it are mounted the rotary magnets, the vertical magnets, and the release magnet. With the release armature moved out of the way, we can see the end of the release magnet. Here we can see the twin rotary magnets and the rotary armature operating and releasing. Here we can see the twin vertical magnets and the vertical armature operating and releasing. Here we have a good look at the motion of the vertical pawl, which when it's in its normal mounted position would be engaging and disengaging with the teeth of the vertical ratchet. Here we get a good look at the action of the rotary pawl, which in its normal mounted position would be engaging and disengaging with the teeth of the rotary ratchet. Here's a good look at the double dog, which engages with the vertical and rotary teeth of the ratchets. Here's a view of the stationary dog. Here's the off-normal finger. And when it pivots, it operates and releases the vertical off-normal springs. Looking now at the lower front part of the switch, we have the lower shaft bearing, the 11th rotary step cam, and these once again are the 11th rotary step springs. Here's a good view of the switch cover plate. And at the back it's hinged to the switch base, and at the front here it's bolted to this switch frame. And it will provide mechanical protection from below and help also to prevent dust from getting in, and provides the rest for the switch cover. On it is mounted this number card holder and the test jacks underneath here that we'll look at a bit later. And beneath the cover plate is this bank assembly, which is not really part of the switch, but it bolts to the switch through these two bank rods. And it is interconnected with the switch by these two wiper assemblies that are mounted on the shaft. Okay, I'm going to talk a bit about the shaft. The shaft is a 10.5-inch long steel rod that runs through the center of the switch, as you can see here. Now the shaft is held in position by two bearings that we looked at earlier, but the shaft is allowed to move up and down inside those bearings, and the shaft can also rotate inside those bearings. Now there's a lot of piece parts attached to the shaft, starting with these two wiper assemblies, the 11th rotary step cam, the rotary ratchet, the vertical ratchet, the normal pin clamp and normal pin, and the shaft spring assembly. So when the shaft moves up and down, all the attached parts move with it. When the shaft rotates, the attached parts rotate with it. Okay, we're looking now at the rear of a switch. This is actually the rear of a partially dismantled part switch that I have. Mounted to the rear of the switch base is this 16-prong plug. Now the plug is mounted via this wooden mounting block which insulates the prongs from the switch base. The prongs are arranged in 8 pairs, and the 2 prongs in a pair are separated by an insulator. Now when the switch is mounted, each prong pair will slide down between 2 jack springs, such that each prong will have electrical conductivity between itself and its mate jack spring. This plug and jack spring arrangement provides all the electrical connectivity between the switch and external circuits, with the exception of succeeding circuits. The switch connects to succeeding circuits via its wipers and bank assembly. Also on the rear is this rectangular can. It contains a protection network, a couple of capacitors and a resistor, and this is used to protect the contacts of the relays that are used in pulsing, such as the A relay contacts and the E relay contacts. And without this protection network, there would be severe arcing on those contacts and they would very quickly burn out. Okay, we're looking now at my test stand. And my test stand will mount a selector switch, and it is used for maintenance and testing purposes. And I constructed this from actual central office shelving units that I salvaged. So the selectors mount into this test stand exactly in the same way they would mount in the central office shelf. This test stand has its own 48-volt power supply and its own rotary dial. In the central office, the selector shelves have jack springs associated with each switch position, just as you see here on my test stand. Here we have 16 jack springs, and they are arranged in pairs so that there are 8 sets. Each pair of jack springs is insulated from each other, and there is a long, narrow slot in between each jack spring. The jack springs are mounted via wooden mounting blocks to isolate them from the iron framework. Each selector shelf position also has 4 protruding lugs. The bayonet slots on the side of the switch base can slide over these lugs to firmly mount the switch into position on the shelf. So here you can see the view looking down at the top of the jack springs on the selector shelf. And as I move the selector into position, you can see how the plug prongs line up with the jack spring openings. And as I move the switch into position and line up the bayonet slots with the lugs, the switch can just slip down over those lugs into its rest position. Here's a view of the switch being mounted into position. You can see the bayonet slot on the side of the switch base being lined up with the selector shelf lug, and the switch sliding down into its seated position. Now when the selector is fully seated, as you see here, the left and right plug prongs of each pair rests in physical contact with their mate left and right jack springs. This provides electrical conductivity between each prong and its associated jack spring. Removal of the switch is accomplished by undoing the two nuts that hold the switch to the bank assembly and simply sliding it up off its jack springs. This plug-and-play arrangement allows for easy removal of the switches for maintenance purposes, since no actual wires have to be disconnected. This is the test jack assembly. It mounts to the cover plate and hangs below the cover plate. There are 4 jack springs. We have the ring and tip and sleeve, which are extensions from the incoming ring, tip, and sleeve leads from the preceding circuit. And the 4th spring is a ground contact. Now in the central office, a technician can plug into these jacks using a butt-in and dial a test call through the switch. Now the butt-ins are usually arranged such that when it's plugged in, the ground contact will be bridged to the sleeve lead, so that the switch will be made busy to all preceding circuits, so that this switch will not get selected while it's being tested by the technician. And here's how the butt-in plug fits into the jack springs. And here's what the butt-in looks like. It has a rotary dial, a talk and monitor switch, a belt clip, and on its other side it has a transmitter and a receiver. And so with the button plugged in, I can go to talk and dial through the switch. So this is a side view of the switch cover, and on the right edge you can see that it has bayonet slots much like the switch base, and so it mounts over the same lugs that the switch base does when it's mounted on the selector shelf. So when the switch cover is mounted in position, it provides protection for all the electromechanical parts in the switch and also helps to keep dust out. And here's what it looks like when it's mounted into position. Here's a front view of the bank assembly that I use with my test stand. The bank assembly bolts to the switch frame through these 2 bank rods, which have threaded ends at the top. The bank has 2 tiers. There's 10 levels on each tier. Each level has a row of upper side contacts, 10 contacts, and a lower side of 10 contacts. So there's a good view of the 10 contacts on the top row of the top tier. Here's a view of the bank assembly upside down. So this is the bottom row of terminals, and this is the underside of the bottom row of terminals. So here we see 20 wire termination lugs. So they are the lugs from the underside and the top side of the bottom row of terminals. Now these wire lugs are where all the wires coming into the bank attach. So there would be 400 of these wire lugs connected to 400 wires. Okay, so this is level 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. This is terminal 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So in each tier there are 10 levels numbered 1 up through 0, and on each level there are the 10 terminals, upper side numbered 1 up through 0, and on the bottom side numbered 1 up through 0. In the top tier, the upper side terminals are the A or F lead special function terminals. In the bottom tier, the upper side terminals are the ring lead terminals. With the bank assembly upside down, in the bottom tier, the underside terminals are the tip lead terminals. And with the bank assembly still upside down, in the top tier, the underside terminals are the sleeve lead terminals. The tip and ring leads provide the voice and signaling transmission path of a circuit, while the sleeve lead provides the control path for holding up the switch train and for providing the busy idle status of a circuit. Okay, so the bank assembly has 100 tip, ring, and sleeve circuits terminating on it. What are these circuits? These are circuits that takes us to the next stage of the switching network. So these are terminations for succeeding circuits. So these could be going to other selector ranks, or to outgoing trunks, or to connectors. So the tip and ring of a circuit are on a specific level and horizontal position. So for instance, this particular one here is on level 0, position 1. And its associated sleeve lead would also be on level 0, position 1, but on the underside of that particular level. So the sleeve lead location also always matches its associated tip and ring location. Now, in a central office environment, bank assemblies do not normally stand alone like the one in my test stand. Instead, there are a number of them multiple together. The most common arrangement is for 10 banks on a shelf to be multiple together. Here we see 2 banks multiple together. The 400 wires on this bank assembly are multipled over to this bank assembly, which in turn are multipled over to the bank next to it, and so on, down for 8 more banks. So altogether there would be 10 banks with the same 400 wires serving the same 100 circuits. Okay, we're going to have a look now at our wiper assemblies. We have 2 wiper assemblies, the lower one with 2 wipers and an upper one with 2 wipers. The lower wiper on the bottom assembly is the tip lead wiper, and the upper wiper is the ring lead wiper. In the upper wiper assembly, the lower wiper is the sleeve wiper, and that's the only one we're concerned with in this video. The upper wiper is for the A or F lead, which are only used for special functions, and we are not going to be discussing those in this video. So we have 3-wire circuits: tip, ring, and sleeve. Now, attached to each wiper is a single wire wiper cord, which get wired up to these terminals below the test jack assembly, and from there at the back they are wired up through the switch and to various switch contacts inside the selector. So that's how the selector switch connects with the wipers. It's through these wiper cords. So we have a ring wiper cord, a tip wiper cord, and a sleeve wiper cord. Now the wiper assemblies are fixed onto the shaft, and as such, if the shaft steps upwards, then the wipers will step upwards with them. Similarly, when the shaft rotates, the wipers will rotate with the shaft. And this permits the wipers to brush against the contact terminals of the circuits. Now, when the wipers have been stepped upwards and rotated and are resting on bank terminals, such as they are here. Here I have raised the shaft to the 10th level on the bank and rotated the shaft into the first terminal. So the wipers here are sitting on position 1 of level 0. When the wipers are at rest on terminals, there is electrical conductivity between the terminal and the wipers. So in this particular situation, the contact terminals on level 0, position 1, are in contact with the wipers on level 0, position 1, and electricity can pass through between the wipers and the contacts. So then this gives us connectivity between the selector switch and the succeeding circuit. So by lifting and rotating the shaft, the selector can access any one of the 100 circuits on its bank assembly. Now the vertical stepping of the shaft is controlled directly by the rotary dial of the calling telephone. Whatever digit is dialed, the shaft will step up that number of steps so that the level that it's going to rotate on will be equivalent to the digit dialed. So for instance, if the customer dials as 0, the shaft will step up to the 0 level and then will trunk hunt or rotary hunt on that level. So when the pulse train of the digit dialed has finished and the shaft has been stepped up to the level of that digit, it will automatically begin to rotate and trunk hunt for an idle circuit. Here is my step-by-step switching system demonstration unit. It has 7 step-by-step switches, mostly hidden here beneath the gray dust-covered cans. On the lower shelf, the leftmost switch is a line finder. It finds the calling telephone's line and connects it to a first selector. The other 2 switches on the lower shelf are selectors, the switches we are going to examine in this video. The left one is a first selector and the right one is a second selector. On the upper shelf are 3 more selectors. The leftmost switch is a third selector, followed by a fourth selector, and then a fifth selector. The rightmost tall switch is a connector. So the demo unit has 1 line finder, 5 selectors, and 1 connector. All 5 selectors are the same type, which is the ED30976, the type we are examining. Their numerical identifier indicates their rank in the switch train, which corresponds to the particular digit in the called 7-digit telephone number that they process. That is the first, second, third, fourth, or fifth digit. I'll place a call through the demo unit so you'll get a feel for the actions of the selectors. The selector has 5 stages of operation. Idle, as you see here, with all relays released, the shaft in its rest position and the wipers in their rest position, and there is no connectivity between this and succeeding circuits. Seized, this is just a quick operation of 3 relays and then it gets into a stable state. Processing, where it responds to dialed digits. Connected, where it has connected a preceding circuit to a succeeding circuit, and release. Okay, so let's just follow a call through at normal speed without any interruption. We're going to dial telephone number 734-5789. So first I'll just go off hook. Line finder finds my line. I get dial tone and dial 7 and then 3. I dial 4, 5, 7, 8, 9. Selector rings the called telephone. The call is answered and a conversation begins between the 2 parties. Then the calling party hangs up and the switch train releases. Okay, now let's take a look at that operation again in more detail, but just up to the point of the seizure of the first selector. The stage you're looking at now is the idle stage. The selectors are in a steady state condition, that is, there are no moving parts, and all parts in the selectors are in their released or normal position. They have not been seized by a preceding circuit and are not connected to a succeeding circuit. They are available to be selected for use on a telephone call. First, I'll take my phone off hook. Going off hook causes the line finder to be seized, and then it moves its shaft vertically upwards and then rotates it as it hunts for my line. When my line is found, the wipers rest on my line terminals on the bank. Let's watch the line finder activity. The line finder is permanently wired to the first selector, but the electrical circuit to activate the first selector is open until the line finder extends my telephone line through itself to the first selector. When it does that, the loop through my telephone line closes the circuit to the first selector and it becomes seized. Seizure involves the operation of the A, B, and F relays, which we'll look at later. First, we'll examine the activity of the shaft and wipers. Okay, now the first selector is seized. I have dial tone and I'm ready to begin dialing. Now the selector is only going to process one digit, and the digit I'm going to dial is a 7. And we're going to focus at this point in time just on the action of the shaft and wipers. And we'll come back later and do a detailed look at all the piece parts that are moving inside the first selector. So this selector is now beginning its processing stage. There's going to be a substantial amount of selector activity as it responds to the reception of the dial pulses by stepping up the shaft and its two wiper assemblies to the 7th level. And then it's going to rotate them in the hunt for an idle succeeding circuit. So I'm going to dial a 7. So I'll rotate the dial, and when I release my finger, the shaft is going to step up as the pulses are received by the A relay in the selector. So here we see the shaft rose up vertically and the wipers are in line with the 7th level of that bank assembly. We can have a look at that again in slow motion. So now that the pulse train of 7 pulses has been received by the selector and it has stepped the shaft up to the 7th level, it's going to automatically begin rotary hunting for a circuit that's idle to the next stage, which in this case happens to be a second selector. Now on the test switch, I have artificially made the first 9 circuit paths busy in order that it will rotate to the 10th position for demonstration purposes. So let's watch that rotary action now. Let's watch that again in slow motion. So here the switch is trunk hunted to the 10th position and the wipers have come to rest on the 10th position terminals, which are the terminals associated with the second selector. I will be describing exactly how rotary hunting works a little later in the video. The first selector now extends my telephone line through itself out onto the wipers to the terminals of the second selector and removes dial tone from my line. The first selector now enters its connected stage. The selector has finished processing and is held in a steady state off normal condition. My telephone line is now extended through to the second selector, which is seized. The operation of each of the 2nd through 5th selectors duplicates the first selector, except for the provision of dial tone. In this video, we are only going to focus on the operation of the first selector, since the other selectors perform in exactly the same manner. When the telephone call ends, the connector initiates the release sequence. In the releasing stage, the connector, selectors, and line finder actively restore themselves to an idle stage by returning the shaft and the wipers to their normal position and releasing any operated relays. Let's watch. Okay, now that we have finished looking at the wiper activity, let's go back up inside the switch and examine the operation of all the internal parts of that switch. We'll begin with selector seizure. Right now, this selector is in its idle state. No relays are operated and all parts are in their normal or released position. So this is the A relay armature. It will operate and in turn operate these contact springs. This is the B relay armature. It will operate and in turn operate these contact springs. And this is the F relay armature. It will operate and in turn operate these contact springs. So I'm going to seize the selector And you can watch, probably the best thing to watch is the contact spring. Sometimes it's a little hard to see the armature operation. Okay, here goes. Let's watch that again in slow motion. So you can see that upon seizure, the A relay operated and remains operated. Following that, the B relay operated and remains operated. And following that, the F relay operated and remains operated. So now this is the seized state of this selector. And that operation took roughly 150 milliseconds to complete. Now, if this is a first selector in the train, dial tone will be flowing through the A relay windings back to the calling telephone, and this selector is ready to receive dial pulses. So now we will begin a detailed look at the relay operations along with other internal mechanisms in the switch. We will not be providing any further information on the F relay, which, although it operates on seizure, it does not perform any functions on non-digit absorbing calls. Neither will we discuss the Z relay, which only functions on digit absorbing calls. Okay, I'm going to dial a test call through the selector. Let's assume a calling party has gone off hook. A line finder has been seized and has found the caller's line and extended it through to this selector. My butt-in will emulate the calling telephone. I'll switch from monitor to talk, which will close the loop. You can watch what happens to the A relay. As you can see, the A relay has operated and has remained operated. At this point, the customer is getting dial tone through the windings of the A relay coils. Okay, now I'm going to dial a 0, and you can watch the A relay pulse. As the telephone dial returns, each time its pulse contacts open and close, the A relay releases and reoperates. Okay, let's watch. Rotating the dial, releasing. Let's watch that again in slow motion. So you can see that the A relay pulsed 10 times, and at the end of the 10 pulses, it remained operated. Those 10 pulses were relayed to the vertical magnet, and so the vertical magnet armature closed and released 10 times, thereby stepping the shaft upwards by 10 steps. Now we'll take a look at the vertical armature action. So here is one of the vertical magnets, the other one is immediately behind it, and below that is the vertical armature. Attached to the front of the vertical armature is this vertical pawl, and you'll be able to watch the action of the vertical armature, the vertical pawl, and the vertical ratchet as I dial a 0. Let's watch that again in slow motion. Now we'll be able to see the net result of the A relay pulsing 10 times, the vertical armature pulsing 10 times, the vertical pawl engaging the vertical ratchet teeth 10 times, and the vertical ratchet stepping up 10 positions. Here we see the shaft and wipers have stepped up to the 10th level, ready for rotary operation to begin. So now we're going to have a look at what happens with the B relay. The B relay operates over the A relay make contacts. So when the switch is seized and the A relay operates, the B relay will follow suit. Let's watch. Okay, here we go. Seizure. There you can see the B relay has operated and remains operated with the A relay. But now let's have a look what happens when we dial 0, because we know that when we dial, A relay is going to release and reoperate once for each pulse. Okay, watch. I'm going to dial 0. Release. Let's watch that again in slow motion. So notice that the B relay stayed operated during the pulsing of the A relay. And this happens because the B relay is a slow release relay, which means that during the interruptions to its energizing current, when the A relay releases, there is insufficient time for it to release before it gets re-energized by the reoperation of the A relay. So this is an intentional design in the B relay because when it first operates, it provides the holding ground on the sleeve lead to the preceding circuits. And we don't want that holding ground interrupted by releases of the B relay. Now we're going to watch the operation of the C relay. The purpose of the C relay is to monitor the incoming pulses and detect when the pulse train has ended. When the pulse train has ended, the C relay will control the transfer of the call from vertical stepping operation to rotary stepping operation. Now the C relay operates after the first pulse is coming through. So when the A relay releases on the first pulse, the C relay will operate. Now it will remain operated during pulsing because it's a slow release relay. When the A relay operates at the end of pulsing, it gives enough time for the C relay to release, and it transfers the switch from vertical to rotary stepping. Let's watch. Okay, I'm going to seize the switch. Notice the C relay did not operate at this time. I'm going to dial a 0, release. Let's watch that again in slow motion. So notice that the C relay operated at the first pulse and that it remained operated during the whole pulse train, and at the end of the pulse train it released. At that time it would transfer control of the switch from vertical stepping to rotary stepping. Okay, now we're going to take a look at the E relay operation. The purpose of the E relay is to control rotary stepping, and it does this by pulsing. When the E relay pulses, it energizes and de-energizes the rotary magnet, which in turn causes the rotary armature to operate and release. The rotary armature operating and releasing causes the shaft to rotate horizontally. The E relay first operates at the end of the first pulse when the shaft has stepped vertically one step. With the C relay operated and the shaft up one step, the E relay operates, and then it just waits for the C relay to release at the end of this train of pulses to begin rotary stepping. Let's watch. Okay, so first we'll see what happens just on the vertical stepping portion of the call. Okay, I'm going to seize the switch. E relay does not operate. Going to dial a 0, release. Let's watch that again in slow motion. So you can see there the E relay came up just after the first pulse and stayed operated for the duration of the pulse train. At this point in time, the E relay is ready to start pulsing on the rotary stepping portion of the call. Okay, now we're going to watch the E relay pulse 10 times, which in turn causes the rotary armature to pulse 10 times, and in turn the rotary pawl to engage the ratchet teeth of the rotary ratchet 10 times, which will turn the shaft and wipers around to the 10th position. Okay, let's have a look at that action now. You're going to concentrate on looking at these contact springs here. Okay, here we go. Pretty fast. I'll slow it down for you. This is still fast, but at least you can see it. Rotary stepping is about 3 to 4 times faster than vertical stepping. It must be completed during the interdigital interval, which is the time taken by the caller to wind up the dial for the next digit. Hunting 10 rotary steps takes about 1/3 of a second. Okay, so here's the rotary armature. The pulsing of the E relay causes the energizing and de-energizing of the rotary magnets. This in turn causes the rotary armature to be operated and released at the same pulse rate as the E relay. Let's watch that action now. Now I'll slow that down for you by performing the task manually. The rotary pawl is attached to the end of the rotary armature. Therefore, it engages and disengages with the teeth of the rotary ratchet at the same rate as the pulsing of the rotary armature. Let's watch the rotary pawl in action now as it engages and disengages with the ratchet teeth 10 times. Again, that's very quick, so I'll slow it down for you by performing the task manually. And looking at the rotary armature from the other side of the switch, here's the rotary armature, and here's the rotary armature lever that works with the rotary interrupter. And during rotary hunting, this lever on the rotary armature is going to operate and release 10 times, which is going to make this contact spring break and make 10 times. Since the rotary interrupter is under control of the rotary armature, it will pulse at the same rate as the rotary armature and the E-relay. Let's watch that action now. Once again, I'll slow that down for you by performing the task manually. The operate path for the E-relay is through the closed contacts of the rotary interrupter. So each time the rotary interrupter opens, the E-relay releases, and each time the rotary interrupter closes, the E-relay reoperates. In this sense, the rotary interrupter controls the E-relay pulsing. On the other hand, the energizing path for the rotary magnets is through the E-relay operated. So when the E-relay operates, the magnets are energized and the rotary armature operates. When the E-relay releases, the rotary magnets are de-energized and the rotary armature releases. In this sense, the E-relay controls the pulsing of the rotary armature. Okay, now we're going to watch the net result of all this pulsing. We saw the E-relay pulsing 10 times, the rotary armature pulsing 10 times, the rotary interrupter pulsing 10 times, the rotary pawl engaging the ratchet teeth 10 times. And now we're going to watch the shaft and wipers rotate to the 10th position. Here you can see the shaft and wipers resting at the entrance to the 10th level, waiting for rotation to begin. So here we go. Pretty fast, and we'll look at that again in slow motion. So now we'll put together the sequence of events that make rotary hunting happen. Rotary hunting is a repeating cycle of events. One complete cycle advances the clockwise rotation of the wipers by one step. So let's begin the description at the start of one of the cycles. Let's say the wipers have just finished stepping to bank terminal position 1, as you see here, and at this point in time the E-relay is released and the rotary armature is released. If the succeeding circuit on bank position 1 is in use, there will be ground on its sleeve terminal. This ground will pass through the contacting sleeve wiper, through the closed rotary interrupter contacts, and through the E-relay winding to battery, thereby operating the E-relay. The E-relay operated energizes the rotary magnets, which causes the rotary armature to operate. The rotary armature pawl engages the rotary ratchet teeth and turns the ratchet clockwise one step. This moves the wipers from terminal position 1 to terminal position 2. Simultaneously to this action, the rotary armature lever opens the rotary interrupter contacts, and this causes the E-relay to release. The released E-relay causes the rotary magnets to be de-energized, which releases the rotary armature. This causes the rotary pawl to disengage from the rotary ratchet teeth and return to its rest position. It also returns the rotary armature lever to its normal position, which recloses the rotary interrupter contacts. So at this point in time, the wipers have just finished stepping to bank terminal position 2, and the E-relay and the rotary armature are both released. This completes one cycle of rotary hunting. This exact cycle will be repeated for each busy circuit encountered. Rotary hunting ends when an idle circuit is found, or when there is no idle circuit to be found. We'll look at those two situations next. The first sleeve bank terminal reached that does not have ground potential on it indicates an idle circuit. Since there is no ground, the E-relay will not operate and rotary motion stops, and the wipers come to rest on the terminals of this idle circuit. This condition allows the D-relay to operate. Let's have a look now at the D-relay. The D-relay only comes up after vertical and rotary stepping is finished and the wipers are resting on an idle trunk. When that happens, the D-relay operates. It transfers control of this switch to the succeeding circuit. It also connects the incoming tip ring and sleeve lead to the outgoing tip ring and sleeve leads to the succeeding circuit. The D-relay also then causes the release of the A-relay, which in turn releases the B-relay, and the only relay remaining operating in the switch during the conversation of the call is the D-relay. Let's watch. You'll hear the vertical and rotary stepping in slow motion in order to get a better sense of when the D-relay operates. All right, seizure, D-relay doesn't operate. Dial a 0 and release. And there, after the rotary stepping had finished, the D-relay came up. If no idle circuits are found, the selector will step to the 11th rotary position. Since there is no 11th sleeve terminal, the E-relay will not operate and rotary motion will stop. In addition, the 11th rotary step springs are operated by the cam on the shaft. This sends all trunks busy tone to the preceding circuit. If this is a first selector, dial tone will also be removed. The wipers do not provide any further function on this call attempt. Okay, we're going to have a look now at the 11th rotary step operation. And there are two parts involved here. This is the 11th rotary step cam. It's attached to the shaft. And these are the 11th rotary step springs. And they are used when the shaft rotates to the 11th rotary step position. These springs will be operated by this cam, and that will cause all trunks busy tone to be returned to the calling party. Now I've set up this switch so that on the 7th level there will be rotation to the 11th rotary step. So I'm going to dial a 7 and the switch is going to step up to the 7th level and then rotate to the 11th rotary position, and you'll be able to see the action of the cam and the 11th rotary step springs. Okay, so I'm going to seize the switch. I'm going to dial a 7, release the dial. We'll look at that again in slow motion. And as you can see there, the cam turned around with the switch shaft to the 11th rotary position, which then enabled the operation of the spring assembly. That will in turn then disconnect dial tone from the customer and instead replace it with all trunks busy tone, which is typically 120 interruptions per minute and sounds something like Let's have a look now at the vertical off normal spring assembly. These are the vertical off normal springs and contacts. This is the normal pin, and underneath that is the off-normal finger, which is allowed to pivot. So when the switch is at rest, as you can see here, the off-normal finger is held down by the normal pin. And as soon as the switch steps up to one vertical position, like this, then the finger is released and allows the vertical off-normal springs to operate. I'll just show that several times here. So the VON springs operate as soon as the shaft moves vertically off normal. They will stay operated as long as the shaft remains vertically off normal. The operated springs are in the operate path for the E-relay, so they allow the E-relay to operate. The operated springs are also in the operate path of the release magnet, so it will allow the release magnet to operate at the appropriate time. Now, when the shaft returns to normal upon release, the VON springs will also return to normal, which will cut off the operating path for the release magnet and allow the release magnet to release. Okay, now we're going to have a look at the two assemblies called dogs. And the first dog is the stationary dog, and the second dog is called the double dog. So we'll take a look first at the stationary dog, and the stationary dog is called that because it doesn't move. This is the stationary dog, and as you can see, it has an arm that initially fits into a channel in the vertical ratchet, and as the vertical ratchet moves up and down, then that groove allows for operation uninhibited by the stationary dog. So it just slides up and down inside that channel. The purpose of the stationary dog is to support the shaft when it's in a combined vertical and rotary off-normal position. Here we see the shaft has been raised to the third level and is also rotary off-normal. You can see that the stationary dog is engaged with the vertical ratchet teeth and allows for smooth rotary motion of the shaft while at the same time providing vertical shaft support. The stationary dog provides this support whenever the shaft is rotary off normal. This includes during clockwise shaft rotation on trunk hunting, during stable rotary off normal shaft positions on connected calls, and during anti-clockwise shaft rotation on releases. Okay, we're going to turn our attention now to this apparatus, which is called the double dog. And as the name might suggest, there are two parts. The top part is called the vertical dog, and the bottom part is called the rotary dog. And this apparatus is allowed to pivot on a hinged pin, as you can see here. Now, when the double dog is in its normal position, there is a gap here between the vertical ratchet teeth and the vertical dog, and there is a gap here between the rotary ratchet teeth and the rotary dog. Now, on the first pulse of a call, when the vertical armature operates to step the shaft to its first vertical position, this action will allow the vertical dog to engage the vertical teeth on the vertical ratchet, and the rotary dog to engage the rotary teeth on the rotary ratchet. These dogs will remain engaged in the ratchet teeth for the duration of the call until the switch releases. I'm going to dial a 1, and you can watch how the two dogs react to that digit being dialed. So now you can see that the vertical dog is engaged into the teeth of the vertical ratchet, and the rotary dog is engaged into the teeth of the rotary ratchet. The purpose of the vertical dog is to engage the vertical ratchet teeth so that as the shaft is stepping upwards, it will not slip back down between pulses. Watch the action of the vertical dog as I dial a 0. Let's watch that again in slow motion. As you can see, it keeps engaged with the teeth as the ratchet steps up and stops it from slipping back down. So now let's take a look at the operation of the rotary dog. The purpose of the rotary dog is to prevent anti-clockwise rotation of the shaft during rotary hunting, and also to prevent anti-clockwise rotation of the shaft whenever the shaft needs to be held in a rotary off-normal position, such as during a connected call. Whenever the shaft is in a rotary off-normal position, the shaft spring tension tries to make the shaft turn anti-clockwise. So when it's rotary hunting, when the rotary pawl disengages between pulses, the shaft would turn anti-clockwise unless it was stopped by the rotary dog. Let's have a look at a call where we're going to watch the rotation of the shaft on level 7. Okay, so I've dialed a 7 and the shaft has stepped up to the 7th level and is ready to rotate. So let's watch the action of the rotary dog as the shaft rotates. So let's watch that again in slow motion. As you can see, the rotary dog remained engaged with the rotary teeth to prevent anti-clockwise rotation of the shaft during the rotary hunting portion of the call. Now the rotary motion is stopped and the shaft is held in this rotary off-normal position by the rotary dog. This condition will be maintained until the end of the call, when the switch release activities are initiated and the rotary dog disengages from the rotary ratchet teeth. This allows the shaft to return to its rotary normal position. We'll be looking at that release activity in just a short while. Now the double dog is forced into engagement with the ratchet teeth by this vertically mounted spring called the double dog spring. This is a very high tension spring and it maintains the pressure on the double dog to keep it engaged with the ratchet teeth. So let's take a look at how the double dog gets actuated. Here the bottom of the double dog, and it has an extension arm coming back into here, and at the top of that extension arm is this tooth sticking up. And on top of that tooth is a plate, a spring assembly plate that's resting on top of it. And you can see that it has a rectangular hole inside of it. When the dog is released, that rectangular hole fits over this tooth and keeps the dog away from the two ratchets. So here's the released position of the dogs, and now you can see that that little spring assembly is sitting over the tooth, and it keeps the dog from moving or engaging with the ratchet teeth. Now that little latch plate, by the way, its actual name is the release link. So the release link will move upward under force from or pressure from an arm on the vertical armature. So on the first pulse, when the vertical armature operates, it will move the release link up and disengage it from the double dog tooth. So I'm going to dial a digit 1, and you can watch the operation of the release link. So there you can see the release link came up, it disengaged from the tooth and now just rests on top of it, and the double dog was forced against the ratchet teeth. So we're going to take a look now at the release magnet and armature operation. The release magnet is energized at the end of an established call when the D relay releases, and on an abandoned call when the A and B relays release. So here is the release magnet, and this is the release armature. When the release armature operates, this allows a pin at the bottom of the release armature to push against this tab on the double dog. That moves the double dog away from the vertical and rotary ratchets and allows the shaft to rotate anti-clockwise and then to drop down to its normal position. When the double dog is pushed by the pin on the release armature, it allows the release link to relatch over the tooth of the double dog to keep it maintained in a position away from the vertical and rotary ratchets. So I have an established call here with the wipers resting on level 0, position 0. So let's see what happens to the release armature when I hang up the call. We'll watch that again in slow motion. There you could see the release armature operated, pushed the double dog away from the ratchet assembly, which allowed the shaft to rotate anti-clockwise and then to drop down to its normal position, and also for the release link to re-engage over the tooth of the double dog to maintain it in its rest position away from the ratchet teeth. Here's another point of view. Notice that prior to release, the vertical dog is engaged with the ratchet tooth on the right side, while the stationary dog is engaged with a ratchet tooth on the left side. When the release armature operates and the vertical dog separates from the ratchet tooth, the stationary dog maintains the shaft support during the anti-clockwise rotation of the shaft. When the shaft reaches its rotary normal position, the stationary dog resides in the vertical ratchet channel, allowing the shaft to drop vertically under its own weight. As the shaft approached its normal vertical position, the normal pin struck the off-normal finger, causing the VON springs to release. This de-energized the release magnet, allowing the release magnet armature to return to normal. We'll have a look at this action in slow motion. So one other thing to talk about on the release of the switch is how do we stop the anti-clockwise rotation of the shaft? Well, that's controlled by this normal pin. When the normal pin rotates anti-clockwise with the shaft, eventually it will slam up against this tab on the shaft spring bracket, and that's what stops the anti-clockwise rotation. So let's watch that action now. Presently, the shaft wipers are resting on the 10th terminal of the 10th level. So now I'm going to release the switch. We'll watch that again in slow motion. Okay, and as you can see here, the normal pin is now resting against the shaft spring bracket. So we're going to look now at the shaft spring assembly, which consists of the actual shaft spring cap, and the shaft spring bracket. Now the shaft spring is attached to the shaft spring bracket down here in this little hook, and it's attached to the cap at the top. The cap is attached to the shaft, so when the shaft rotates, the cap will rotate. The shaft spring bracket, however, does not rotate with the shaft because it's looped around the back through this normal post. So the normal post prevents the bracket from rotating with the shaft. So that means that when the shaft rotates, we have the bottom of the spring fixed here, the top of the spring fixed to the movable cap. So as the shaft rotates, the spring will tension up. It'll wind up and create tension. And this tension is used to rotate the shaft anti-clockwise when it's time to release the shaft at the end of a call. So we'll take a look at the operation of the shaft. I'm going to manually rotate the shaft here, and you can see that as the shaft rotates, the spring cap rotates with the shaft, but the shaft spring bracket remains motionless. So the spring winds up as the shaft rotates clockwise. And if I let go of this, the tension on that spring will cause the shaft to rotate anti-clockwise, and then it'll drop down by force of gravity to its normal release position. This concludes my video of the single-digit processing application of the step-by-step selector. For my other telephony videos, search YouTube with Lenny the Phone Guy, including the quotation marks. Thanks for watching.